Let us start the lecture. Bismillahir-Rahmanir-Rahim. Today, our topic is work done. We will derive an equation for the work done on the two-row wheel of velocity compounded steam impulse turbine. You know that this type of steam turbine where one in one ring of nozzles is installed, and just next to nozzles, instead of one row of rotating blades, there are two rotating blades, complete two rows of rotating blades installed on one wheel, and in between two rotating uh, wheel rows of two rotating wheels, there is one ring of stationary wheels, stationary blades. It is hanging in the casing up. So this is called as two-row velocity compounding. Two-row wheel, and it is called velocity compounding because velocity is distributed, velocity is dropped in the moving blade in two stages. First in one row and next in another row. You know, in impulse turbine, there is no pressure drop in the moving blades because of their design. In between two moving blades, here is the structure, and here is the velocity, here is the wheel, one row of nozzles in the beginning, and there is moving blade, one row of moving blade, and their direction of is downward view, and next is uh, a row of fixed blades, and their direction of curve is upward, concave upward, and after fixed blade there is another moving. So there are two rows of moving blades, and in between them is one row of stationary blades. Stationary blades function is only to change the direction when steam flows out of the first row, and then direct the steam into the entrance to the second row of the moving blades. So here is pressure profile. You can see pressure drop takes place only in the nozzle. All pressure drop takes place in the nozzle, and velocity drop, velocity increase, maximum velocity increase. Full pressure drop in the nozzle and maximum velocity increase from 0 to CAI maximum. It is takes place in the nozzles. Once at the it exits from the nozzle with full velocity, it enters into moving blade. In the moving blade, continuously the velocity decreases. Then comes stationary, rows of stationary blades. In rows of stationary blades, there is a very little drop in the velocity, but major velocity drop again takes place in the next row of moving blade. So velocity drop takes place in two rows of moving blade. That's why it is in two stages. So at the end, velocity, there is some residual velocity because we need to get out of, steam should get out of the turbine. For that, it needs certain velocity. It cannot be zero, but it is desirable that velocity should be minimum because leaving steam will take away kinetic energy. So that kinetic energy loss is called as lost velocity, V square by 2, VE square by 2. This is shown in this diagram. What we are going to do is to show that total work done on this type of wheel, that is two-row velocity compounding, is equal to m dot Cb delta Cw delta Cw1 plus delta Cw2. Because of this, we can see that this is total velocity whirl component. Delta Cw, change in whirl component of velocity in moving blades 1, and change in whirl component of the velocity of the steam in moving blade row number 2. Delta Cw1 plus delta Cw2. This is the total change in the whirl component of velocity in the two wheels, and multiplied by Cb, it gives you per kg work done because of this whirl component. But m dot multiplied by m dot will give you total power output of moving blades. total power, a total rate of work done on the moving blade by the steam. Here is the velocity diagram of this system. You can see A, B, C. A, B, C is the velocity diagram. A, B velocity diagram at the inlet to the blade, one row of first row of moving blade, and their angles are shown. Hello, are you with me?
Yes, sir.
Okay. Acha, A, B, C is the velocity triangle at inlet to the moving blades, and A, B, D is the velocity triangle at the outlet of the moving blade. Now this is shown how steam leaving the first row of moving blades enters into fixed blade. So you can see that this is the CAE exit velocity of moving blade. It will enter to the fixed blade, and this is CAI2. Now exit, after exiting from the fixed blade, it will enter into the next row of moving blade, which is velocity triangle EFG. So EFG, in EFG, CAI1, this is the CAI1, and this is the direction of CAI1 exiting from the fixed blade. So it will enter into the moving blade, next second row of the moving blade, and this is alpha. This is the angle of velocity, absolute velocity, alpha I2. So here subscript 2 means second row of moving blade, and here in this triangle subscript 1 means this belongs to first row of the moving blade. So with the help of these two sets of diagram, you can understand what happens in first row and what happens in the second row. So delta CW1 is this one, CD, the length CD. This is the whirl component of the velocity, delta CW1, and in second row of the blade, delta CW2, GH, this GH distance, this is the, so how it is done, these angles, actually when you design a velocity triangle, you have to draw it with the geometry box tools. So you need a scale, you need a protector, and with the help of a scale and protector, you draw these lines to the scale. You need a scale graph paper with millimeter graph paper, and that paper to the scale. If AB is given, you draw AB to the scale. If this angle beta is given, you draw this angle. Then you draw alpha is given, you draw this angle. When you draw one side AB and these two angles of second and third side, you will get triangle ABC. So this is how velocity triangles are drawn. And if they are to the scale, you can measure what is CAI, what is CAI2, what is alpha, beta, things like that. So whatever is given, we enter. Whatever is not given, we calculate or measure with to the scale. Now we'll go to next part, how to derive this. So we will derive this according to certain assumptions. Here, for your convenience, since diagrams are not very clear, they are blurred. You cannot read where is CB, where is CAI1, where is CAE1. So here I have written elaborately symbols with their A, B, C, D, E, F, G, H, whatever number I have given them. According to that, these things are defined. So all angles, all sides of the triangles, blade angles and velocity angles, they are all given here. Delta CW is given here. These are the symbols. Now in figure 11-12, which I have shown you above, so there are three velocity diagrams are shown. Number one, velocity diagram of the first row of the moving blades, ABC, then velocity diagram of the fixed blades, thus only velocity entering and leaving the fixed blade is shown, and velocity diagram of the second row of the moving blades, that is this diagram. So this EFG and EFH, this is at the second row, and this is ABC and ABD, these are the velocity diagrams at the first row of the moving blades. So their notations are further elaborated here. Clearly, if it is not clear in diagram, you can read from here. And here is the derivation, very simple in 2 steps. Our purpose was to derive this equation. What is the total work done on the wheel by the steam? What is the total work done by the wheel on the steam? Very simple. In simple impulse turbine, single stage impulse turbine, we have shown that work done in the first row is equal to m dot Cv delta Cw. Cv delta Cw is the work done on the wheel by the steam. So m dot se multiply kar दें, this is total work done by the steam on first row of the rotating wheels. Similarly, on second row rotating wheels, m dot Cv is common, m dot is common in both the wheels, but delta Cw is different. Here is delta Cw1, here is delta Cw2. So in first set of triangles, second set of triangles, we have mentioned here. So we have work in the 2 wheels, so we combine it. When we combine it, this work done in first row plus work done second row, then we get this m dot Cv delta Cw1 plus delta Cw2. So this was the objective. But for that we have such a long preparation. We have to understand how velocity, what is the construction? What is the construction of the 2-row wheels of impulse turbine? This is called velocity compounding, and this is also called Curtis turbine. So this was a Curtis turbine, and this is how we draw blade diagram. This is how we draw velocity and pressure.
वो आगे उसको भी अंदर रख देना.
Mute your mic. Don't talk with each other. Mute your mics, please. Individual mic should be muted during the lecture. Don't disturb the lecture. So now, then we have learned how to draw velocity triangle at first row of the blade, velocity triangle in the fixed blade in between, and there's no, in the second row of the moving blades, this is the velocity diagram. Once, if you can't read these symbols and notation, you can further see here. And I have written with Word document. This is very clear. When you get copy of this, you can see and read it. So then we have just applied this formula that work done on a steam blade is equal, rotating steam blade is Cv multiplied by Cw, delta Cw. So Cv multiplied by delta Cw in one row. So Cv multiplied by delta Cw2, another row multiplied by mass flow rate. In दोनों को add कर दिया, we get equation 1113, and this is the equation of total work done on 2-row wheel of Curtis turbine. So for this, with this is over now, and time is only a couple of minutes are remaining. So I can show you another one. Another document. So here our objective was how to find out maximum diagram efficiency of 2-row wheel of the velocity compounded steam impulse turbine or the Curtis turbine. So we have already done this for simple impulse turbine or deliver turbine. Maximum diagram efficiency का formula हमने derive किया. So इस case में our objective is to do these 3 things. 1, 2, 3. First objective is to derive the relationship for maximum diagram efficiency of a 2-row wheel velocity compounded steam impulse turbine. And second objective, and this is the formula eta d. Eta d means diagram efficiency, and this is called square alpha I1. Any alpha I1, this is the absolute velocity entering to the first wheel ka square. So diagram efficiency is square. Maximum diagram efficiency is at this angle. If velocity angle is this much and its cos square alpha is this, then that at this value of cos square alpha I, we will get maximum efficiency. And if we put diagram efficiency equal to this, then we will get rate of doing work per unit mass flow rate is equal to 8 CB square. In single wheel simple impulse turbine, it was 4 CB square, and it is 8 CB square, and multiplied by 2. So now, this was the second objective, equation 1115 and 1116. These need to be derived. And here is the diagrams. This type of diagram you have seen for simple impulse turbine also, but these values were different. Here was cos alpha by 2, here it is cos alpha by 4. What is this? This is value of CB upon CI. This is the optimum value of CB upon CAI. If you will run steam turbine or Curtis turbine with 2-row velocity compounded wheels, then you need to keep CB upon CI equal to cos alpha I 2 divided by 4. And its maximum value of eta d will be equal to cos square alpha I, alpha I1, cos square alpha I1. It was mentioned in that equation. So this is the graphical presentation, cos square alpha I1. So graphical presentation is this, and solution will be done inshallah next time, because time is over. So we must stop here our meeting. CR, hello, listening to me? Can you talk to me, CR? Are you listening to me?
Yes, sir.
Participants are not very much. There are only 9, including me. There are 10 participants, and I hope you will note their name and send me. So I'm taking print screen, but anyhow, you should make attendance also. So, okay, thank you very much. And our meeting is over now.
सर बारिश हो रही है कराची में?
हाँ बड़ी तेज बारिश हुई है, अभी नहीं हो रही, कल हुई है, कल शाम को हुई है और बड़ी बारिश सैलाब आया हो।